Here's the part the brochure never leads with: in an electric car, the single most expensive thing you're buying isn't the motor, the screen, or the badge, it's the battery. Roughly 30 to 40% of the whole price of the car is just that one component sitting under the floor. And it doesn't only set the price. It decides how far you can drive, how fast you can charge, how the car behaves in the cold, and, frankly, whether it's safe. So you'd think there would be one best battery that everybody uses. There isn't. There's lead acid, nickel metal hydride, 3 or 4 flavors of lithium-ion, sodium-ion, solid-state, lithium-sulfur, even hydrogen fuel cells, and every one of them is a different set of trade-offs. The honest truth is there is no single best battery. There's only the right tool for the job. So in this video we're going to read the spec sheet on every one of them, and then tell you what it actually means. Before we open up the chemistries, let's be clear about why this little box matters so much. A pack is just thousands of identical cells wired together, so whatever the cell can do, the whole car inherits. Pick a cell with high energy density and the same sized pack carries you further on a charge, that's your range. Pick a cheaper cell and the car gets cheaper, because remember, this is a third or more of the bill. Pick a cell that tolerates fast charging and you're back on the road in 20 minutes instead of an hour. And pick a cell with a stable chemistry and the car is far less likely to catch fire if it's crashed or abused. Range, price, charge speed, safety, for completely different things, and all of them are decided by the chemistry inside one cell. That's why engineers obsess over it, and that's why the rest of this video is organized around the cell. To compare batteries fairly, we need one scorecard, and we'll use it on every chemistry in this video. 9 numbers. First, energy density, how much energy you store per kilogram, in watt-hours per kilogram, and per liter, which is watt-hours per liter. One golden rule here: a single cell is far denser than the finished pack, often by 1.5 to 2 times, so we'll always tell you which one we mean. Second, charge time, how long from 10 to 80%, the part you actually wait for. Third, power, or discharge rate, written as a C rate, how hard the battery can push for acceleration. Fourth, cycle life, how many full charges before it fades to 80%. Fifth, cost, in dollars per kilowatt-hour. Sixth, cold and temperature tolerance, because batteries hate winter. Seventh, safety, how easily it overheats, what engineers call thermal runaway. Eighth, self-discharge, how fast it leaks charge just sitting there. And ninth, raw materials, whether the world can actually supply them. Keep these 9 in your head, they're the lens for everything that follows. Strip away the marketing and every battery on this list works the same basic way. There are 3 players. The anode, the negative side, which holds the charge-carrying ions when the battery is full. The cathode, the positive side, which wants those ions back. And between them an electrolyte, the medium the ions swim through, with a thin separator that stops the 2 sides from touching and shorting out. When you discharge, when you drive, the ions leave the anode, drift through the electrolyte to the cathode, and that movement pushes electrons around the outside circuit, through your motor. When you charge, you force the whole thing into reverse, the ions go back home to the anode, ready for the next trip. That's it. A battery is a rechargeable ion shuttle. Everything else in this video, the energy, the cost, the safety, the cold weather behavior, comes down to which ion is shuttling, what the anode and cathode are made of, and whether that electrolyte is a flammable liquid or something safer. We start with the granddad of them all, lead acid, invented back in 1859 and still in the car under your bonnet today. The chemistry is simple: lead and lead dioxide plates sitting in sulfuric acid, about 2 volts per cell. Its numbers tell you everything. Energy density is just 35 to 40 watt-hours per kilogram at the cell level, the lowest on this entire list. Volumetrically it's 80 to 90 watt-hours per liter. A full charge takes 6 to 12 hours, and it survives only 200 to 500 deep cycles before it's done. On the plus side it's dirt cheap, somewhere around $75 to $175 per kilowatt-hour at the cell, and it's genuinely very safe. It gases hydrogen rather than bursting into a lithium fire. It's also the most recycled product on Earth, around 99%. So why isn't your EV running on it? Because of that energy density. To match a normal lithium pack, a lead-acid traction pack would weigh 5 to 6 times as much. You'd be hauling the weight of a second car. That makes it physically impossible for range, which is why it's completely dead for traction. Its future is narrow but secure. It lives on as the humble 12-volt auxiliary battery, even inside electric cars, plus forklifts, backup power and off-grid storage. Next, nickel metal hydride, the battery that quietly powered the entire hybrid revolution. The chemistry is a nickel oxyhydroxide cathode and a metal hydride alloy anode in a potassium hydroxide electrolyte, about 1.2 volts per cell. At the cell level it stores 60 to 120 watt-hours per kilogram, a big step up from lead acid, and 140 to 300 watt-hours per liter. It charges in roughly 1 to 3 hours and is famously abuse-tolerant and very safe. But here's the honest catch, and it's a big one, that cell number flatters it. Take the Toyota Prius pack, 168 cells, 201 volts, about 1.3 kilowatt-hours weighing 37 kilograms. Do the maths and the pack is only about 37 watt-hours per kilogram, roughly half the cell figure, because hybrid packs are built tough for shallow, repeated cycling rather than deep range. It also self-discharges fast, 10 to 15% a month unless it's a low self-discharge type. On cost we'll be honest, the figures floating around, roughly $250 to $500 per kilowatt-hour, are only partly verified, so treat them as a guide. Its role was the bridge between lead-acid and modern lithium, and that bridge is now closing. Toyota moved the 2024 Prius to lithium-ion, ending the NMH hybrid era. Its future is legacy hybrids and your rechargeable AA cells. Now we reach modern lithium-ion, and the first big one is NMC, nickel, manganese, cobalt. What makes NMC special is that it's tunable. Engineers can dial the recipe from a balanced 1-1-1 mix toward high nickel blends like 8-1-1. Manganese stabilizes the structure, nickel is where the energy comes from. So more nickel means more energy density, but, and this is the trade-off, less thermal stability. At the cell level NMC stores a strong 150 to 220 watt-hours per kilogram, with the high nickel 8-1-1 cells reaching 260 to 290, and around 600 to 680 watt-hours per liter. It charges 10 to 80% in about 25 to 35 minutes, lasts 1,000 to 2,000 cycles, and at pack level runs around $128 per kilowatt-hour. Thermal runaway begins around 200 to 210 degrees. Now the honest problem, cobalt. It's expensive and it's an ethics headache. The Democratic Republic of Congo supplies about 75% of it, and prices spiked from $24,000 to $53,000 a ton in 2025 on an export ban. That cost and that conscience are exactly why the industry keeps pushing nickel up and cobalt down. NMC remains the workhorse of most premium and long-range EVs. Volkswagen, BMW, Hyundai, Kia, Ford's Mach-E and GM's Ultium all lean on it. The last in this chapter is NCA, nickel, cobalt, aluminium, and you can think of it as NMC's high-energy cousin, the chemistry Tesla and Panasonic made famous. The recipe is roughly 80% nickel, 15% cobalt, and 5% aluminium, where the aluminium does the stabilizing job that manganese does in NMC. Because it leans so hard on nickel, NCA delivers the highest energy density of any mainstream chemistry on the road, 200 to 260 watt-hours per kilogram at the cell, with the very best reaching about 300, and around 676 watt-hours per liter. It charges fast, roughly 20 to 30 minutes, and modern cells last 1,000 to 1,500 cycles, up from about 500 in the early days. It costs a premium over NMC. NCA is the signature of Tesla's cylindrical cells, the 18650, the 21700, and the new 4680. But here's the honest trade-off, and it's the recurring theme: all that energy comes from all that nickel, and high nickel means lower thermal stability. NCA's thermal runaway can begin as low as 150 degrees, making it the least stable of the mainstream lithium chemistries. And one caveat to plant firmly: you'll see the number 322 watt-hours per kilogram quoted for Tesla cells, but that figure is unverified, so we won't claim it. NCA is the choice when you want maximum range per kilo and you're willing to engineer hard around the safety. Lithium iron phosphate, LFP, is lithium-ion, but with an olivine cathode made of iron and phosphate instead of cobalt and nickel. For years it was dismissed as the cheap, low-energy option. Then it came roaring back. The old cells managed only 140 to 160 watt-hours per kilogram, the latest ones hit 190 to 210 at the cell, and structural packs push system energy higher still. Volumetric energy sits around 424 to 450 watt-hours per liter in a blade cell. On charging, the honest picture matters. Mainstream fast charge is 10 to 15 minutes from 10 to 80%. You'll have seen the headlines, CATL's 3 minutes 44, BYD's 400 kilometers in 5 minutes. That engineering is real, but it needs a megawatt-class charger and a car built to take it. Your everyday top-up is more like 15 to 30 minutes. Cycle life is its quiet superpower, 3,000 to over 5,000 cycles, far beyond nickel chemistries. Cost is the headline. LFP packs have fallen to around $81 per kilowatt-hour, the cheapest on the market. And it's the safest mainstream cell, with thermal runaway onset around 270 to 300 degrees, because olivine bonds don't readily release oxygen. The one real weakness is cold, where it can drop to half its range. It now powers standard-range EVs and dominates grid storage. So why did a chemistry everyone wrote off suddenly take over? 3 things, and notice that none of them changed the basic recipe. First, the patents expired, the core LFP patent in 2017, the carbon coating one at the end of 2022, which unlocked global manufacturing and crushed the price. Second, structural packs. BYD's Blade and CATL's Celta pack designs threw away the wasted space inside the old module impact layout, recovering most of the energy LFP gave up at the cell level. Third, cathode densification lets cells charge at 4C and beyond. Put together, the latest LFP is a different animal. The cell holds 30 to 40% more energy than the old version, the pack holds 60 to 80% more usable energy, it charges 3 to 4 times faster, and it lasts about twice as long. Same iron and phosphate, smarter packaging and cleaner manufacturing. That's the real lesson. Sometimes the breakthrough isn't a new element, it's getting out of the chemistry's way. Sodium-ion swaps the lithium for sodium, an element that's 500 to 1,000 times more abundant, sitting in ordinary salt. It pairs a hard carbon anode with a layered oxide or Prussian blue cathode, and uses aluminium current collectors on both sides instead of copper, which is one reason it's cheaper to build and ship safely at 0 volts. On energy density it's modest, 100 to 160 watt-hours per kilogram, with CATL's new Naxtra cell reaching about 175, so at its best it roughly matches LFP, no more. Where it shines is everything else. Charging is genuinely fast, around 5C, cycle life is extraordinary, over 10,000 cycles. And it owns the cold, at -40 degrees it still delivers about 90% of its capacity, beating every other chemistry here. Now the honest catch you'll rarely hear in the marketing. Sodium-ion is not yet decisively cheaper than LFP. Cheap lithium through 2023 to 25 erased the cost gap, and LFP fell to around $81 per kilowatt-hour. The gap may reopen, but today it's close. It's real and shipping. JACZway was the first mass-market sodium EV, CATL's Naxtra hit mass production in December 2025, and its strongest near-term fit is grid storage, city cars, and cold climates. Solid state is the one everyone's waiting for. The idea: replace the flammable liquid electrolyte with a solid one, a ceramic, sulfide, or polymer, which then lets you use a pure lithium metal anode that stores roughly 10 times the charge per gram of graphite. That's the energy jump. Prototype and lab cells show 350 to 500 watt-hours per kilogram, with a volumetric target of 800 to 1,000 watt-hours per liter, sample charge times around 10 to 12 minutes, and lower fire risk. But, and this is the honest part, there are 3 problems nobody has solved at scale. 1. Dendrites. Lithium grows whiskers that pierce the solid and short the cell. 2. Interface resistance. Getting solid to touch solid well enough that ions flow. Mercedes needs pneumatic actuators just to squeeze the stack. 3. Cost. Dry rooms and brittle ceramics push it to $400 to $600 per kilowatt-hour, 4 to 6 times today's lithium-ion. So here's the number to carry. There are 0 all-solid cells in any customer car in 2026. Only semi-solid cells are on the road, and even those have stumbled, with NIO halting its and SAIC's MG4 launching a semi-solid in December 2025. Mercedes drove a prototype EQS 1205 km on one charge, a proto, not a product. Realistically, tiny batches around 2027 to 8, volume near 2030, cost parity not until 2032 to 35. Treat firm dates and the word fireproof as hype to discount. Lithium-sulfur trades the metal oxide cathode for plain sulfur, paired with a lithium metal anode, and works by conversion chemistry rather than the usual ion shuttling. The prize is the energy by weight, a theoretical 2,600 watt-hours per kilogram, about 5 times lithium-ion. In practice the ceiling is nearer 500, and shipping cells from Lighten land around 310 to 360. Even that is excellent per kilogram. But here are the two catches you must keep on screen. First, volumetric energy is weak, 350 to 555 watt-hours per liter, because sulfur is light but bulky, so the cell is featherweight yet takes up a lot of room. Second, cycle life is short, only about 250 to 300 cycles, because of the polysulfide shuttle, where dissolved sulfur species drift across and bleed away active material. Charging is slow too, and the lithium metal anode brings dendrite risk. On the plus side, sulfur is dirt cheap and abundant, with no nickel, cobalt or manganese. So it wins first where weight beats volume and you don't need thousands of cycles, drones, electric air taxis, satellites and defense. Lighten, backed by Stellantis, is building a Nevada gigafactory for 2027. It is not coming to your sedan first, and any 700 to 1000 watt-hour figure you see is a target, not a shipping cell. Hydrogen belongs in this video so we can be clear about one thing, it is not a battery. A fuel cell is a converter, a PEM stack that combines hydrogen from a 700 bar tank with oxygen from the air to make water and electricity. You don't recharge it, you refuel it. Toyota's Mirai carries a 330 cell stack and 3 carbon fiber tanks holding about 5 kilograms of hydrogen. And here is its genuine superpower, you refuel in 3 to 5 minutes and get 575 to 700 kilometers of range, no waiting at a charger. Pure hydrogen is wonderfully energy-dense by weight, 33 kilowatt-hours per kilogram, though the heavy tank drags the system down to around 1.4. But the catch, the one that decides everything, is efficiency. Well to wheel, you keep only about 25 to 35% of the original clean energy, because you pay a tax at every step, making the hydrogen, compressing it, then converting it back to electricity. A battery EV keeps 70 to 90%. That means hydrogen needs 2 to 3 times the clean power per mile. It's also expensive, around $33 to $36 a kilogram, and today roughly 60% of hydrogen is gray, made from natural gas. So it won where refueling speed and constant duty matter, forklifts, heavy trucks, and buses. But it lost the car. Shell closed all 7 of its California light-duty stations in early 2024. Hydrogen is a fuel for freight and fleets, not a battery for your car. Before we compare chemistries, let's talk shapes, because the same chemistry behaves differently depending on the can it lives in. The oldest EV cell is the cylindrical 18650, 18 mm wide, 65 tall, basically a fat AA, holding maybe 9 to 13 watt-hours. Tesla grew it to the 2170 in the Model 3 and Y, and then the squat, fat 4680, 46 by 80 mm, around 86 to 100 watt-hours, and stiff enough to help hold the car together. Then there's the prismatic, like BYD's blade, a long flat aluminium sword, nearly a meter long, that lies flat across the floor. And the pouch, a flat foil laminate rectangle with 2 tabs, the best packaging per cell, though it needs a frame to squeeze it. Keep these shapes in mind, they decide how much of the chemistry's energy you actually get to use. Now zoom out from the cell to the whole pack, because this is where a quiet revolution happened. The classic design stacks cells into modules, then modules into a pack. Tidy, but those module walls waste 30 to 40% of the volume. The first leap was cell to pack, skip the modules, drop cells straight into the pack. CATL's Chilean pack reaches 72% volume use and 255 watt-hours per kilo at pack level. BYD's blade goes further, the cells are the structural crossmembers. The newest step is cell-to-body, like Tesla's 4680, the cells are the floor, and the seats bolt straight on top. Tesla claims 370 fewer parts and 14% more range. Treat that as a claim, not a verified number. The lesson is one you'll hear all video: a humbler cell in a smarter pack can beat a fancier cell in a wasteful one. This is exactly how LFP, with lower energy at the cell level, clawed back competitive range. The packaging shrank while the chemistry stayed cheap and safe. This is the heart of the whole video, every chemistry on one matrix, so let's walk it row by row. Lead acid, 35 to 40 watt-hours per kilo, dead for traction, too heavy by a factor of 5 or 6, surviving only as your 12-volt auxiliary battery. NMH, better, abuse-tolerant, but it powered the hybrid era and is now exiting. Toyota moved the 2024 Prius to lithium-ion. NMC, 150 to 220 watt-hours per kilo, the workhorse of most EVs, tunable but burdened by cobalt cost and ethics. NCA, the highest mainstream energy, 200 to 260, Tesla's cylindrical signature, slightly less stable, more range. LFP, lower energy but the cheapest at $81 a kilowatt-hour, the safest, and the longest lived at 3 to 5,000 cycles, the standard range and grid king. Sodium-ion, the cold champion, minus 40 degrees and still 90%, with cheap, independent supply, shipping now. Solid state, the promise, 350 to 500 in the lab, but zero in customer cars in 2026. Li-S, superb per kilo, weak per liter, short cycle life, aviation first. And hydrogen, marked with a star, isn't a battery at all, it's a converter you refuel, with refueling in 3 to 5 minutes but a brutal efficiency penalty. Notice what the matrix refuses to give you: no single row is green all the way across. The high-energy chemistries cost more and run hotter, the cheap, safe ones give up some range, the cold champion is still catching up on price, the headline grabbers live in labs. That tension is the entire story of this video, one table, and genuinely no king. Here's energy density, watt-hours per kilo, at the cell level, and it tells you how light a pack can be for a given range. Lead acid sits at the bottom, around 38, which is exactly why it can't move a car. NMH roughly doubles that. LFP lands near 200, sodium a bit lower at around 140. Then the high nickel chemistries climb, NMC near 250, NCA close to 280. Li-S leaps to roughly 360 per kilo, genuinely impressive, and solid-state tops the chart near 450. But read the asterisk, that solid-state figure is a lab and prototype number, not a shipping product. The one insight here is that the tallest bars are the least proven. The chemistries you can actually buy today cluster in the middle, and as we'll see, weight per kilo is only one of several things that matter. Now flip it to money, dollars per kilowatt-hour, at the pack level, from BloombergNEF's 2025 numbers. This is the chart that actually decides whether you can afford an EV. LFP is the cheapest at $81. Sodium-ion is right beside it at about 87, and that's the honest catch on sodium. Cheap lithium in 2023 to 2025 erased its price advantage, so it is not yet decisively cheaper than LFP. NMC sits much higher at 128, and NCA higher still around 135, because nickel and cobalt cost real money. Then look at the last bar, solid state, estimated at roughly $500, 4 to 6 times today's lithium-ion. That bar, again, is an estimate, not a price tag you can pay. The insight is brutally simple: the cheapest chemistry, LFP, is also one of the safest and longest lived. That combination is why it took over. Cost is what you pay once, cycle life is how long that money lasts. This chart counts how many full charge cycles each chemistry survives before dropping to 80% of its capacity. Lead acid is weakest, around 400 deep cycles, wear it out and you replace it. NMH and NMC sit near 1500. NCA is a touch lower, around 1200. But look at the two that run away with it, LFP at roughly 4000 cycles, and sodium-ion past 10,000. That's the highlighted bar. Sodium can outlast the car around it several times over, and LFP isn't far behind. The single insight here flips the usual story. The chemistries with lower energy density, LFP and sodium, are the ones that last the longest. For a daily driver or a grid battery cycling every single day, longevity often matters far more than squeezing out extra range. Last chart, charging speed, 10 to 80%, in minutes, and here lower is better. One honest note first. Lead acid is shown at 480 minutes, but that's me forcing it onto the same axis. In reality, lead acid charges in hours, not minutes, so treat its giant bar as a stand-in for far too slow, not a literal figure. After that, the modern chemistries are tightly bunched and genuinely fast, NMC around 30 minutes, NCA and sodium near 25, and LFP the quickest at about 12 minutes. That's the surprise. The cheap, safe, long-lasting chemistry is also among the fastest to charge, thanks to recent cathode work like CATL shrinking. One fair caveat: those headline 5-minute LFP charges need a megawatt-class charger and a car built to accept it. In everyday life you're looking at 15 to 30 minutes. Even so, the gap between modern lithium and old lead acid is enormous. So who actually wins each job? Long-range and premium EVs go to the high-nickel chemistries, NMC and NCA, because there, every extra watt-hour per kilo buys range. Standard range EVs, and almost the entire grid storage world, belong to LFP, cheap, safe, and long-lived, which is why LFP is roughly 85% of new stationary storage. Hybrids were NMH's home, though that era is closing. Buses, trucks, and forklifts increasingly look at sodium-ion and even hydrogen, where weight matters less than cost, cold tolerance, or fast refueling. Phones and laptops still lean on high-density lithium-ion. And drones, electric aircraft, and defense are where LiS shows up first, because they're a featherlight pack that only needs a few hundred cycles is exactly the trade you want. The pattern is the whole point. You don't pick the best battery, you pick the right battery for the task in front of you. The history here isn't a clean march forward, it's full of comebacks and quiet exits. Lead acid was invented back in 1859, and astonishingly it's still in your car today as the 12-volt auxiliary battery, even inside electric cars. NMH had its moment in the 1990s powering hybrids like the Prius, but that chapter effectively closed when Toyota switched the 2024 Prius to lithium-ion. The 2010s belonged to NMC and NCA, the chemistries that made long-range EVs possible. Then came the real plot twist. In the 2020s, LFP, an older, humbler chemistry, was reborn, once its patents expired and engineers wrapped it in clever blade and cell-to-pack designs, making it cheap and safe enough to dominate. And in 2025, sodium-ion finally started shipping, bringing genuine cold-weather performance and a cheap, independent supply chain. The takeaway: in batteries, old ideas don't always stay dead. Now the future, but with the hype carefully separated from the dates you can trust. In 2025 and 2026, sodium-ion scales up for real. CATL's Naxtra entered mass production at the end of 2025. Also in 2026, LFP fast charging gets even better. CATL Xinjiang Generation 3 targets a roughly 6-minute charge in shipping cars. Then comes the part to be careful with: solid state, somewhere in 2027 to 2030. Those are targets. Toyota, QuantumScape, Samsung have all named dates and slipped them before, and there are still 0 solid-state cells in customer cars right now. Around 2027, LiS should arrive first for aviation, with Leiden's Nevada plant. And on cost, BloombergNEF forecasts pack prices falling to roughly $80 a kilowatt-hour by 2030, down from about $108 in 2025. So, sodium and cheaper LFP are near-term and real, solid-state is promising but unproven, and prices keep falling either way. So here's the turn, the one thing to carry away. After every chart and every chemistry, there is no king battery, and anyone selling you one is selling you something. Each chemistry is a different bundle of compromises: energy, cost, lifespan, charge speed, cold tolerance, safety, supply. What changes is which compromise fits your job. As a buyer, stop asking which is best and ask 4 better questions. What's the total cost over the life of the pack? Can you actually charge it where you live? How cold does your winter get, and what are you really using it for? For most people, LFP is now the sensible default. cheap, safe, and it lasts. If you need maximum range, high-nickel NMC or NCA earns its premium. Sodium-ion is rising fast, especially in the cold and solid state. It's worth getting genuinely excited about, but on the day it actually ships in a car you can buy, not on the day a press release promises it. Don't let a spec sheet bully you into chasing one number, whether that's peak energy density or a headline charge time, because real-world value lives in the whole bundle, not the tallest bar. Buy the battery that fits how you'll actually drive, charge, and live. Match the battery to the job, that's the entire honest read. And that's the honest map of EV battery technology, lead acid hanging on as your 12-volt helper, NMC and NCA chasing range, LFP quietly winning on cost and safety, sodium-ion arriving for the cold and the grid, and solid-state and lithium-sulfur waiting in the wings with real promise and real caveats. No single best, just the right tool for each job. If you want technology explained this way, with the hype stripped out and the trade-offs left in, subscribe to Technologia today. Hit the bell so the next deep dive finds you, and tell us in the comments which chemistry you'd put in your own car. We read the spec sheet, then we tell you what it actually means.